Dear colleagues, good afternoon for everybody. We will start our second plenary session. And the first speech was organized by Mr. Yang, China, about the cooperation between Taizhou Research Institute and Chernivtsi National University. Please, Mr. Yang, begin. I'm sorry, Christy Liu, you are ready?
Well,刘婷可以听到我声音吗？Dear academician, Untitled and distinguished experts, good afternoon. I'm Yan Wenjun, the Dean of the Research Institute of Zhejiang University, Taizhou. I'm very honored to take part in this Correlation Optics International Conference online. I believe that this conference will further strengthen the ties between our institute and all the participants here, and especially promote the exchange and cooperation between the institute and the Chernivtsi State University. And it will open a new chapter for both of us. Now, please allow me to introduce some basic information of the institute to you. Research Institute of Zhejiang University, Taizhou, is mainly focused on comprehensive applied research, jointly established by Taizhou government and Zhejiang University. It's founded in 2007 and the first local research institute established by Zhejiang University. The research institute is located in Taizhou, a beautiful city on the coast of the East China Sea. This is a medium-sized city dominated by manufacturing. The private economy here is booming. The industry, such as automobiles, machine tools, pellicles, electrical machinery, and molds, have a solid foundation, which is well known international, aiming at the local industrial and the advantages, the sublines of Zhejiang University. 10 research centers were set up, including electric mechanics, optoelectronics and information, electrical and control, energy and environment, and materials science and engineering. We have got 170 full-time staff, including more than 30 high-level talents, such as doctors, professors, and associate professors. A national-level postdoctoral research workstation and graduate practice base in Zhejiang province were built. Engaged in applied technology research and development and achievement transformation, we have carried out more than 800 scientific research projects in the fields of intelligent manufacturing, new materials, electronic information, central. 180 invention patents. Sorry. 100 invention patents have been obtained, more than 20 of which have achieved industrialization, ranking as one of the top 10 scientific research institutions in Zhejiang province for patent application. In the field of optoelectronics engineering, the institute has successfully cooperated with well-known enterprises such as Crystal Optoelectronics, Dongmeng Group, Weixing New Materials, Boxing Electronics Center. A number of industrial online testing equipment were developed and formed into a relatively complete product series. The results of machine vision technology was integrated and applied in the research and development process of intelligent equipment, such as sorting machine of quartz wave, appearance defect, less navigation AGV, automatic Scala center. Therefore, the institute is remarkable for one of the research and development highlands of machine vision technology in Zhejiang province. In 2019, we have the honor to introduce academician Untitled and set up a modern optical technology center with academician Untitled as the chief scientist. After he took office, he has visited some well-known companies such as Crystal Optoelectronics and Weixing Optics. These companies show strong interest in his research results, and we hope to carry our more scientific research cooperation in the future. In addition, academician Untitled also published 7 high-level papers, which enhanced the academic influence of the institute in the field of modern optics. We would like to express our sincere gratitude to academician Untitled for his great contributions. Ladies and gentlemen, the Research Institute of Zhejiang University, Taizhou, is currently in a period of rapid development. I sincerely hope to have more exchange and cooperation with you and work together to promote the widespread application of outstanding achievements in modern optics in the manufacturing industry. I'm looking forward to your visit to our research institute after the epidemic. Thank you.
Thank you for your nice presentation. Are there any questions? So I am on behalf of Rector of University. Would like to thank Mr. Yang for his nice presentation about cooperation between Chernivtsi National University and Taizhou Research Institute. And I hope that our cooperation will be more fruitful and more strength. Thank you once more for your nice presentation about our work. If there are no questions, there is a next talk. It will be presented by Professor O.Angelsky, the chair of the conference, from correlation to singular optics. Please.
The title of my report, From Correlation to Singular Optics. Dear colleagues, our conference has a long history since 1991. It is growing both in number of countries. The main topic that are covered during the conference, and I would like to present my vision in development of basic scientific approach from correlation to singular optics. Proceeding from the subject of research presented here, singular and correlation optics, I will reiterate the words of Professor Michael Berry, the pioneer of these studies. Professor Berry says that among all the physical and mathematical sciences, he falls in love with optics, that this area of research allows to visually observe physical processes and natural phenomena. And this is the best way to make sure of the validity of the provisions, statement, and assumptions. That is why, as I will illustrate my report with live examples, the results of our research. As it is known, the classical section of optics consists of geometrical wave optics and the optics of scattering media. With the advent of lasers and coherence radiation, quantum, correlation and singular optics, nonlinear and coherent optics are developing. The subject of correlation and singular optics, the study of which I am directly involved, is the properties and regularities of the formation and propagation of complex inhomogeneous structural optical fields. Correlation optics operates with probabilistic characteristic of a complex field based on the use of statistical models and methods. Correlation methods are used in the theory of coherence and polarization of light fields. It operates with space-time correlation function of the second order to assess both the spatial and the temporal coherence of the field and the polarization properties of light. The intensity, correlation, and polarization of the optical field are interrelated by certain parameters. They are expressed in terms of the known combination of elements of the Wolf coherence matrix. For example, the spatial coherence matrix of the second order is given as you can see from this relation, where this is the elements of coherence matrix and this is the components of the electric field strength, and provides a transition from the parameters of the optical fields to the correlation function, which can be directly determined using an interference study. Unlike correlation optics, singular optic studies define structure of the field. Look at figure E here. You can see numerous micronutrients typical for regular light waves with a feature of spatial distribution or amplitude or phase or polarization of light in the grains and between them. These formations, named as singular, their spatial distribution, the regularities of alternation, occurrence, and annihilation during the propagation of a complex light field are the subject of singular optics. Here you can see the speckle field obtained in monochromatic here and polychromatic radiation. Since this approach, the optical field is characterized by certain networks. The nodes of these networks contain singularities and or stationary points of one or another field parameter. These singular structures, vortices in a scalar field, polarization singularities in a vector field, have unique physical features. In particular, the phase is not defined in the center of the vortex. The shape of the phase front of such a structure is helicoidal. Here you can see the distribution of intensity here and phase in the vicinity of the vortex here. The intensity and phase values are marked with corresponding color. You can see here and here respectively. Phase from in the vicinity of the vortex you can see here and here respectively. And here you can see the vortex, the behavior of the field near vortex center. Due to this, the Poynting vector circulates around the center of the vortex, forming the so-called orbital angular momentum. In the vector field with elliptical polarization, the end of the vector of electric field strength is circulated. The circulation of the transverse components of the Poynting vector is realized as well. This leads to the appearance of the spin angular momentum you can see here. Such features of singular structures open up new possibilities for development of unique optical equipment. For example, optical tweezers, devices for capture, moving and controlling of micro and nano objects. Here you can see in this figure, you can see the distribution of the transverse component of the Poynting vector, indicated by arrows in a circularly polarized. And now, once again, about correlation optics. Let's refer to the following figure. Thus, the concept of correlation is used to describe the characteristic of randomly distributed parameters of the optical field, both in space and in time. Figure A, at the figure A, you can see the intensity distribution obtained in the case of interference of two slits. The figure B, intensity distribution obtained in the case of interference of three slits, where amplitude zeros appear at separate points. You can see these points here. Figure C, phase distribution in the case of interference of three slits, where there are zero amplitudes, points with a phase change in the range of from 0 to 2 pi. And figure D, is the example with two phase singularities of opposite signs. A set of statistical and correlation parameters serves the degree of difference or a similarity of random process. At the same time, the determinism of physical processes, the connection between cause and effect, is masked by chance. The approach of singular optics removes this contradiction to a certain extent. It can be argued that any space-time distribution value of physical parameter, two-dimensional or three-dimensional, is characterized by a system of singular or spatial points. These points can be networked by a set of lines. Such a network forms the skeleton of spatially distributed parameters. It makes possible to predict the value of this parameter at any points in space at the probabilistic level. Thus, the randomness of the change of this parameter is leveled. I will illustrate the essence of this statement with an example that clearly reveals the idea of singular approach. Here you can see a specific function that reaches two maximums and one minimum within a given interval. The connection between these extremes is carried out by dependent section where the function changes monotonically. Therefore, knowing the coordinates and values of neighboring extrema by interpolation, it is possible with a certain degree of probability to predict the value of this function and various points of the functional dependence. Here you can see two maximum and one minimum. In this sense, the system of stationary points of a function forms its skeleton. Naturally, when analyzing singular networks, everything is much more complicated, but the essence of approach remains the same. Singular networks, which correspond to different characteristics of the wave, are interconnected in one way or another. Generally speaking, we can talk about the relationship between all parameters of the wave. In particular, it can be used as the basis for the development of new algorithms for recovering the field phase from the results of the intensity distribution analysis. Let me give you a concrete example of our results confirming this assumption. The figure shows the intensity and phase distribution of a random speckle field. Here, singularities and stationary points of the field intensity are marked. The distribution of intensity gradient lines corresponds to the regions of the quasi-stationary phase. White lines are intensity gradient lines. Green, saddle of intensity points, yellow intensity maxima, blue and red, absolute minima, vortices of different signs, and here additional minima. Here you can see the relationship between the networks of stationary intensity points and phase singularity points. The connection between the networks, which characterizes by the phase and intensity distribution is demonstrated, indicates the consistent behavior of the distribution. In particular, with a probability of 95 to 98%, saddle point of intensity are localized within a region of rapid phase change. In this case, the lines of intensity gradient, which begin at the saddle points, connect the adjacent vortices of the phase with the topological charge of different sides. That is, analyzing the intensity distribution, we can draw a conclusion about the phase distribution in the field. The presence of topological features such as non-zero topological charge or index leads to the fact that singular beams are more resistant to perturbations in inhomogeneous media. It makes them attractive in optical communication system compared to the smooth waves. It should be added that differences in the signs of topological charges of singular optical beams automatically cause the orthogonality of the orbital angular momentum of such beams. Now let's move to the demonstration of our results. The first video shows the rotation of microparticles captured by an elliptically polarized Gaussian beam, which is carried out due to the mechanical action of the spin angular momentum. The presence of such features of the field opens up prospects for the development of new approach for measuring the parameters of micro and nano objects. For example, the speed of rotation of a particle is associated not only with the characteristic of laser radiation and the structure of existing field, but with the properties of the object. It is determined by induced spin angular momentum and is related to the complex absorption index of the object material. Here you can see the circular motion of particles placed in circularly polarized Gaussian beam confirms the existence of the spin points. Another example of the mechanical action of the coherence light on an object is the influence of an evanescent wave on a birefringent microplate floating freely on the water surface. The size of quasi-square microplate is about from 10 to 15 microns. It has been experimentally shown that under the total internal reflection of a linearly polarized prone beam with an azimuth of polarization of 45 degrees, a transverse component of the optical force of a evanescent wave appears and at the birefringent microplate interface and is perpendicular to longitudinal component caused by the action of the pointing vector. Here you can see the direction of the force which act on the particle. Scheme of experiment demonstrating the appearance of the transverse components of the evanescent wave excited by a linearly polarized incident wave with a polarization azimuth of 45 degrees at the birefringent plate-air interface. The appearance of the transverse power components is caused by the extraordinary transverse spin angular momentum of an evanescent wave. It leads to direction motion of the plate at a certain angle to the longitudinal directions. Note that obtained results indicate the possibility of forming and controlling systems of micro F nano objects. Here you can see the motion of microplate under the action of evanescent wave, rotating and rectilinear motion of the plate when we use the laser power of 1 volt, retaining the plate into its original position within the laser off. Here, the results of creation of such systems by the example of the formation of air bubbles of micrometers in an aqueous suspension containing pigment nanoparticles are presented. Bubbles can stably exist inside or near the illuminated area while being exposed to thermal and optical forces. The control over their position is carried out by the change of the parameters of laser radiation. This method provides controlled creation, existent, targeted transportation of bubbles. Here you can see controlled formation and manipulation of microbubbles in water. Next, let's talk about new approach to diagnostic of the field characteristics that are formed as a result of scattering of coherent radiation. Thus, we have proposed an approach based on the use of carbon nanoparticles for correlation optical diagnostics of optical spectral field. These speckle fields are formed as a result of light scattering and diffraction of laser radiation on a rough surface. Carbon nanoparticles, 10 nanometers in size, which were selected to study the speckle field, were characterized by bright luminescence. Particles suspended in aqueous solutions. The luminescence of these particles made it possible to register the coordinate distributions of intensity minima, singularities, in real time. An algorithm for reconstructing the intensity distribution of a scalar optical field through the analysis of coordinates of nanoparticle is proposed and implemented. By using the Hilbert transform of the speckle field, intensity distribution, the phase distribution in the field is reconstructed. Here you can see the figure for diagnostic of, which illustrates diagnostics of the structure of an optical speckle field using carbon nanoparticles. In conclusion, I will show the results that illustrate how optical singularities manifest themselves in the transition from a monochromatic wave to a real polychromatic field. One of the most striking manifestations of spectral singularities in nature is the effect of spectral coloring of the sun or a mood observed through the various types of light scattering media. This phenomena can be simulated using a light scattering medium, a weakly scattering frost glass. The figure shows the image of the luminary A without frost glass, B and C frost glass with different average heights of micro roughness. As a result of interference exclusion of certain spectral components from the radiation passed through such a medium, we have obtained the results image of the luminary in different colors. These results you can see from these figures. Another example of implementation and interference diagnostics of vortices in white light can serve as interference experiments carried out in a polychromatic speckle field. As a singular forming element, a plate of birefringent crystal is used. Zeros of the field amplitude were achieved for all spectral components of visible light which are coincide in localization. You can see here and here. Diagnostic of polychromatic vortex. Figure A. Distribution of the field intensity in the vicinity of polychromatic vortices. Dark areas here and here localized near the center of these vortices. Interference vortex diagnostic. Figure B. The difference direction of interference flux here and here indicates different signs of topological charge of these vortices. These singularities were observed in crossed polarizers. They were diagnosed as interference, and it can be seen from the chromatic flux oriented in opposite directions. Thus, the combined application of the approach of correlation and singular optics opens up broad prospects for the study of unique optical phenomena and the development of new optical equipments. Note that in the presentation, I tried to use the research results published in scientific journal, where we could not only talk about them, but also illustrate them in live. That is why I choose the online journal Optic Express. At the end of the report, I will demonstrate examples that testify to the international recognition of Ukrainian scientists working in the field of correlation and singular optics. Hope this is part of our efforts. So, on the territory of Ukraine in Chernivtsi for 30 years, 15 international conference correlation optics were held, which were attended by scientists from 32 countries of the world. This allowed us to be kept in the scientific circles to establish an extensive network of contacts. This is evidenced by citation of publication of our scientists, among which, first of all, it is necessary to highlight the scientists of the Institute of Physics of the National Academy of Science of Ukraine, scientists from our Chernivtsi National University, Odessa National University, Institute of Physical Optics of the Ministry of Education and Science, Bliokh. Just a year ago, the editorial board of one of the world's leading scientific publishing platform, Frontiers, in our case, Frontiers in Physics, invited us to be editors and authors of special thematic issue called Singular and Correlation Optics. An example of the interest of the scientific community in the topic under discussion is the work published here. Structured light here, paper Structured Light, Ideas and Concepts. This work was read more than 5,000 scientists from 29 countries. Summing up, it can be argued that such scientific direction as correlation and singular optics in development and progressing. Here you can see the example of this paper published in Frontiers in Physics, and here you can see that this paper is among the 28 paper, the most viewed publication from whole platform Frontiers, the third scientific platform, which had 1 billion 400 million publications. The number of views of the scientific topic singular and correlation optic is 22,000. That corresponds to the about 15% of the most viewed papers of all topic Frontiers. Thank you very much for your attention.
And now, please, questions. Thank you for your attention. And now we will pass to another speaker, Wang, Optical Transfer Matrix, Matrix Correlation as Frequency Domain Analysis of Polarization Imaging System. Please, Professor Wang, please start.
Hello, can you hear me?
Yes.
Okay, good.
Yes, everything okay.
Okay. Good morning or good afternoon, everyone. Okay. And first of all, I would like to thank Professor Angelowski for your kind invitation. It's always my great honor to come back to this correlation optics conference and to introduce our recent work. As shown in this title, okay, today I would like to talk about the optical transfer matrix, okay, which is just matrix correlation as a frequency domain analysis of polarization imaging system. Polarization imaging has attracted more and more interest due to its unique ability to detect the polarization-related information of the object. Okay. Polarization imaging has been applied to many different areas. Okay. Here I show some example. For example, the astronomic observation, agriculture, medical imaging, and also some applications in the remote sensing for the geology. So here just shows the outline of today's talk. So in today's talk, first I will give a brief review of Scala imaging system. Okay, and I will try to just give a general treatment of imaging system and its frequency response for the incoherent image. Then I will switch to the frequency analysis of polarization image system. That is the purpose of this talk. Okay. Then just introduce the diffraction limited incoherent polarization imaging, and then introduce a new concept referred to as the generalized pupil matrix. Okay. Based on this generalized pupil matrix, I will just show you the aberrations of the polarization image and the effects on the frequency response. Finally, I will show you several examples on the newly proposed optical transfer matrix to explain the different sources of errors in polarization imaging system. So here, basically, for the polarization imaging system, they may have these three different sources. One is from the errors from the polarization elements itself, and also the aberrations from the imaging lens, and also some errors or from the during the assembly process. So that is can be referred to as the assembly errors. Before introduce introduction of the polarization imaging, first let me just have a brief review of the conventional Scala imaging system. So this here, I would like to use, just Joe Goodman's, very famous textbook, Introduction to the Optical Optics, or Fourier Optics, as an example to explain the imaging formation. Okay, so usually in applied optics, okay, we often use a black box as a system method to describe the imaging formation. Once we have the object, this object, the light, so its diffraction, okay, enter the black box. Okay, the black box itself has been used to represent the imaging system. Okay, so for this black box, we have the entry pupil and the exit pupil. Okay, so then after the light passing through this black box, okay, the light has already been modulated. Then through another propagation, okay, with a distance of Zi, the light arrived at the imaging plane. Okay, so we will have an image at the image plane. So this is the physical process for image formation. The equation, okay, governing the image formation has been given in this way. So the intensity of the image, okay, is proportional to just a convolution. Here the convolution is has the two functions. One is the system's point spread function. The other is object transmission coefficient. So basically, in the spatial signal domain, the image formed during the after passing through the imaging system, okay, can be represented as the convolution of the object and the convolution of the systems, the function. So this is the signal domain representation for the image formation. On the other hand, we are also interested in the frequency response. Okay, for the frequency response, especially for the incoherent image, okay, usually the Fourier spectrum of the image, okay, can be represented in this way. Here, this is a product of the two terms. Okay, the product of two terms. In this equation, here the star represents the correlation. Okay, this the T, capital T, represents the Fourier transform of the object's amplitude transmission coefficient, and the K, capital K, represents the Fourier transform of the system's point spread function. Okay, through this, this just a linear relationship, we can directly relate, okay, the object information with the recorded image. So here, the correlation plays an important role to describe the system's performance. So as most of you are familiar with the optical transfer function, OTF. The optical transfer function itself, okay, basically is a correlation or normalize the correlation function of the system's response, impulse response. here, this is the correlation, just the calculation calculation. For just the diffraction limited system, the capital K itself can be derived from the pupil of the optic system itself. Okay, the pupil, sometimes we often use the X pupil to represent the performance of the K. As you have already seen from the right side of this figure, okay, the optical transfer functions, okay, of optical system, okay, specify how different spatial frequencies are handled by the system. Okay. Since it's first proposed in 1940s, okay, the optical transfer functions has already been widely used to describe the performance of imaging system for Scala optics. Our interest here, okay, is just the polarization imaging. Okay, so here once again, okay, now what I would like to use a black box, okay, to represent a polarization imaging system. As you see in this black box, okay, we have at least two elements. One is the imaging lens. The other is a polarizing element, like in this way. So same as before, the object, okay, the point source with a polarization information will have the diffraction and enter the black box through the entrance pupil. Okay, after the polarization, just modulation by the polarizing elements and also by the the imaging lens. Okay, then the light passes through the entry pupil. So at the entry pupil, the light has already been modulated, okay, due to its diffraction and also due to its polarization modulation. Then after the diffraction, okay, the light has been focused to the imaging point. So therefore, at the imaging plane, we are able to detect the Stokes image. Okay, Stokes image. So that is the whole process of the polarization imaging system. So here we will use this this figure to represent a generalized model of a polarization imaging system. So through this just the figure, okay, once again, okay, we can just extend the conventional scalar imaging to the polarization Stokes image. Okay, so in the frequency domain analysis, we can represent this, just the Stokes image at the imaging plane by a linear product of the matrix of the polarization imaging system and the object Stokes, the Stokes parameters of the object. Okay, object. Here, this S is a Fourier transform of the Stokes parameters, and here this just represents the Frobenius norm of the whole system of the matrix or the vectors. So this is the whole process for the polarization imaging system. Okay, so just as the optical transfer matrix, okay, just as the optical transfer function for characterization of imaging system, here we would like to propose the optical transfer matrix to describe the performance of polarization imaging system. Okay, so basically here this M is just the proposed optical transfer matrix, and this is just as you see from this definition here, the P itself is the generalized pupil matrix of the polarization imaging system, and here this symbol represents the chronic product, and the A is the unitary transformation matrix. Okay, so as you see from just this equation, and the numerators of this optical transfer matrix, is a matrix correlation of the generalized pupil matrix in the form of a chronic product. Okay, it means that by replacing the product of the, in the chronic matrix product. Okay, we just replace the product by a correlation. So therefore, we are able to calculate the, the numerators for this part. And the denominators of the optical transform matrix is normalized of the matrix itself. So through this way, okay, the optical transform matrix can be defined. Okay. So now let me just show you some examples. Okay. So for let's say just for a polarization imaging system, okay, in our this system, let us assume that okay, in this system we have a one lens and one linear polarizer, okay, with its transmission along the vertical direction. Okay. So through the, let's say, through the just Jones matrix, okay, we are able to write the amplitude transfer matrix in this way. Here, this P, okay, gives just the action of this imaging system. Here, this is the Jones matrix. So through this way, we are able to write the, let's say, the generalized, this just the generalized pupil functions. That is the amplitude transfer matrix. Okay, if we try to change the coordinate by this way. So this just show you an example. Okay, so here from as for a linear polarizer, okay, we have the Jones matrix. Okay, the rest of elements are 0. We only have the one element along the YY component, okay, in this matrix. And this just matrix has already been just been filled with pupil functions. So we have this just the column structure. So once we got the amplitude transfer matrix, okay, through the definition of optical transfer matrix, okay, we can usually plot, just calculate and plot the optical transfer matrix when a linear polarizer has been inserted in this imaging system. So here just show you example. Okay, so as expected, okay, for the element M0, M01, M1, and M11, okay, we have the typical cone structure. Okay, this is for the elements, and the rest of part of the elements are equal to 0. So if we compare with just a Mueller matrix for this, for this system, okay, we can quickly see that. Okay, the conventional Mueller matrix just provide the DC information of this newly proposed the optical transfer matrix. So Mueller matrix is only the DC. So besides this DC component, we also have the other frequency, spatial frequency for in this optical transfer matrix. Okay. Now let's see. So in this figure, okay, I try to show you the relation between the, let's say, the polarization aberrations and the generalized pupil matrix. Okay. So in here, just show you the figure. Once we have the point source, this point source will just generate an ideal, spherical surface, okay, to enter the entrance pupil. No matter the entrance pupil or exit pupil, okay, there will just have the spatial filter, okay, and with only the the central part pass through the system. And during this, just in the center area part, the light will receive its diffraction and also the polarization modulations by all these elements in the imaging system. So at the exit pupil, we will have another just wavefront. Okay. Now let's see. Ideally, if the wavefront at the exit pupil is a Gaussian spherical surface, okay, we will have a perfect point image at the image plane. This is the ideal case. But unfortunately, due to the diffraction or due to any other, just aberrations in the system, okay, the wavefront at the exit pupil has already been distorted, has been changed. Okay, not only the wavefront itself has been distorted, but the polarization state on this wavefront has been changed. I see. For ideal case, okay, idea is for this spherical surface, okay, we will have a uniform polarization state of along this just spherical surface. But unfortunately, due to the aberrations in the in this system, okay, the wavefront and the polarization state has been changed. So as you see in the right side, for the actual wavefront, okay, the polarization state has been changed. So for the different locations, we will have a different state of polarization. So through this way, we are able, to just explain the polarization aberrations and the generalized pupil matrix. As we just see in the definition for the optical transfer matrix, once we are able to have the generalized pupil matrix through the matrix correlation, we are able to find the corresponding optical transfer matrix for the whole polarization imaging system. So based on this just figure, okay, we are able to represent the generalized pupil matrix in this way. Here, P, okay, represents the matrix. The matrix itself, okay, has all this just can be understood as the product of all these terms. Okay, the first one, this P, okay, italic P, represent the pupil function. Okay, that gives the aperture of the system itself. This P. This A just gives us the amplitude change. So it is the attenuation of the whole system. Here W, the exponential W represents the phase difference of the wavefront as compared with a reference spherical surface. So W gives the gives the phase difference. That is the so far that is the conventional just generalized pupil functions for the optical system. Okay, this is conventional one. So here for the proposed generalized pupil matrix, okay, besides this skeleton, we will have another mu Jones matrix at the right side. Okay, this Jones matrix will take care of the polarization related, okay, the aberration. So all the changes from the related to the birefringence in the system or related to polarization will be controlled by this Jones matrix. So this is the generalized pupil matrix. Okay. Now in this slide, I would like to show you the different sources of errors in the polarization image system. So first, let's see. Okay. As I just explained before, for any polarization imaging system, we should have at least two elements. One is the image length. The other is the polarizing element. At least we need two, maybe more. Okay. So based on the different sources, okay, the aberrations of a polarization imaging system can be classified into these three different sources. Okay. The first one, okay, that is it is similar to the conventional Scala imaging system. Okay, we have a different aberrations from the image length itself. Okay, so here the aberrations, okay, includes such as focusing error, tilt of wavefront, spherical aberration, astigmatism, field curvature, distortion, coma, and the higher order of aberration. Okay, so this this type of aberrations stemming from the image length itself. And this is the first type. Okay. The second source of the error is from the polarization elements. So here I have a list of some errors from the polarization elements, including the transmission error of the polarizer. Okay, as you see, the polarizer itself is made of the polymer film. The polymer film, okay, just it sometimes cannot give the perfect polarizing. Okay, so there's a transmission errors of the polarizer. Okay, and for the wave plate, okay, usually just we consider it as a flat, but during the manufacturing, okay, it may have certain, the flatness error and the parallelism error of the wave plate, and also have the angle of incidence for the wave plate. So all these will construct the errors from the polarization elements. Okay, so this is the second type of errors. Okay. The third type of errors, we can call it the, let's say, the assembly error. This error, okay, is related to the relative positioning between the lens and the polarizing elements, okay, between these two different elements, okay. For example, okay, the wave plate tilt, okay, the rotational alignment error of the polarizing elements. So these are all related to the assembly process for this just polarizing imaging system. So therefore, we just we have these three different sources of errors in the polarization imaging system. But in this talk, okay, just due to the limited time, I cannot give all the complete descriptions for all these type of errors. I will just select several ones to show you how the optical transfer matrix can be used to describe all these the aberrations in the polarization imaging process. Okay, first let us see the first type of the error also from the imaging lens itself. Okay. When you see this slide, you can quickly just know that for the in the conventional Scala imaging system, okay, we can just decompose the wavefront, okay, into the wavefront, the aberration into the polynomials in this way. Okay, so here we have the piston, okay, and the field dependent phase, and tilt, and defocus. This is sometimes this is the lower order, first order or third order, and we also have the the fifth order aberrations that is called the saddle aberrations, okay, including the spherical aberration, comma, and the astigmatism, field curvature, and distortion. Okay, we also have the higher order terms. Okay, higher order terms. So this is exactly the same as the as the conventional optical transfer function. Okay, transfer function. Okay, so this figure just show you the the figure to represent the spherical aberration, and here shows another figure to represent the comma, and here shows the distortion. Okay, this is two type of distortion. Okay, as I said, due to the time, okay, I cannot give all these different fifth order aberrations and its effect to the polarization imaging system. Okay, so here I will choose the astigmatism and the field curvature as one example to show you how we can use this the optical transfer matrix to describe the aberration from the imaging lens itself. Okay. So this is figures to represent the astigmatism. Okay, astigmatism. So you can see the let's say the origin of the astigmatism during the imaging process, and this figure shows the field curvature. Okay, field curvature. All these are just are the fifth order of aberration. Okay, and in the optical design and manufacturing, okay, astigmatism and the field curvature and these two types of aberrations are always studied together because they share the similar mathematical expressions. So usually these two types of the aberrations can be studied together. So for the wavefront, okay, the astigmatism and the field curvature has a typical just the wavefront of the saddle structure. Okay, this is the saddle structure for the aberrations of the for the wavefront for the astigmatism and the field curvature. Okay, once this type of the aberrations are come from the imaging lens itself. Okay, so we are able to write this this astigmatism and the field curvature. The first part is the same as the conventional Scala case, and if let's say in this system we have only one wave plate inserted in the imaging in the polarization imaging system. Okay, this Scala function will product Jones matrix for this for this wave plate. Okay, this wave plate. Okay, so here just shows the generalized pupil matrix for the imaging for the polarization imaging system with the astigmatism and the field curvature. So once we have this generalized pupil matrix, okay, we are able to calculate the optical transfer matrix. So here just to show you the example when the system has the astigmatism and the field curvature. Okay, in this example, okay, here we have used the quarter wave plate and the F number for the imaging system takes H, and the let's say the astigmatism, the coefficient is 1 over pi. You will see that. Okay, so see that. So here, let's see, in this, in the M0 and M11, we have the main cone peak, and for the M33 or M32 or M23, oh, sorry, and M32, we also have a cone. Okay, and here we also have give you the phase information. Okay, this is the case when when the astigmatism is equal to 1 over pi. If we increase this, the coefficient for the astigmatism, okay, you can see that. Okay, now, the cone become, asymmetric. Okay, the cone. So this is, for these, elements, you will see that the cone structure has already been changed, and also the phase term has already been changed. So if we increase this parameter, let's continue. Okay, once we still continue the parameters for the astigmatism and the field curvature, you will see that the phase become more and more, irregular, and the peak for the, for the optical transfer, the peak for the element of optical transfer matrix, okay, become narrow. So this is the, this is the case for the astigmatism and the optical and the field curvature. Okay. So when this calculation has been just been carried out, okay, we choose the the F number is 8. Okay. But for the, let's say, especially for the microscopic imaging system, microscopic polarization imaging system, we have the higher view of angle. So therefore, the F number is smaller. In this case, you will see that this type of astigmatism and the field curvature become more serious. So you will see that, besides we have the, for the same parameter of the astigmatism and the field curvature, the peak itself has been changed the shape. Okay, and let's say then it will become narrow and narrow. The face will become more irregular. So finally, we will have this, these three figures represent the optical transfer matrix. Okay, for the astigmatism and the field curvatures. Okay, for the, with a small f number. Okay, so this is one example. So in this, in this example, okay, we just use the astigmatism and the field curvature to represent one type of aberrations. Okay, from the image lens itself. Okay. As I just explained to you just before, okay, besides the, let's say, the image lens, okay, some errors are from the polarizing elements. So here I will show you another example. So this is related to the flatness of the wave plate. So this type of the error is also a kind of manufacturing error. So as you see, so if the wave plate itself are not perfect flat, okay, we have just a curvature of this just wave plate. So here we can use the delta to represent the relative, just the flatness of the wave plate. Okay, so for this, for the flatness of the wave plate, okay, we can write the generalized pupil matrix in this way. Okay, so here, the generalized pupil matrix itself, has already the face along the x component and the y component has already been modulated due to the different thickness of the wave plate. So this, because we use this one as our generalized pupil matrix. So once we have this generalized pupil matrix, okay, we are able to calculate the optical transfer matrix. Okay, as you see here. For this example, okay, when the F number is 2.8, okay, 2.8, you will see that the delta is 1 over 8. When this the parameter is 1 over 8, okay, we have this, the optical transfer matrix, okay, for the one for just a wave plate, quarter wave plate inserted into the system. Okay. Here we can see here just very clear, just a cone in these 4 elements of optical transfer matrix. Okay, let's say if we continue to increase let's say the curvature of the wave plate, you can see the performance. Okay, let's see. When delta is equal to 0, okay, we have a typical cone structure. Okay, without that is the typical just diffraction limited optical transfer matrix. Okay, without aberration. But once we increase the the curvature of the wave plate, this the element of optical transfer matrix become more and more narrow. So this is the effect of the flatness of the wave plate to the polarization imaging system. So similarly, besides besides the flatness of the wave plate, okay, we can also use a similar way to describe the parallelism of the wave plate. So here, during the manufacturing process of the wave plate, okay, the wave plate, sometimes cannot be manufactured as a perfect, with a perfect parallelism. Okay, there are some kind of inclined surface for this wave plate. So here we use the inclined angle alpha to represent the parallelism of the wave plate. Okay. Now let's see it's just generalized pupil matrix. Okay, so because this is the inclined angle, okay, for alpha, so we can represent this just generalized pupil matrix in this way. In this way, through the definition, now we are able to see that. So we are able to study the effect of parallelism of the wave plate to the polarization imaging system. As you see, this is the example. Okay, one example for just a quarter wave plate inserted into a system. Here we choose the F number is 2.8, and the inclined angle is 10 micro arc second, very tiny, very tiny. So it has already become a high quality, wave plate. Even such kind of high quality, wave plate, we can see still, the aberrations. Okay, still aberrations. So if we just increase this inclined surface angle alpha, we can see they are just change. So this is a figure shows the effect of parallelism of wave plate to polarization imaging system. So by increasing the alpha, you will see that the phase change has more serious change for the phase term, but the shape of the amplitude change is so small. So it means that, let's say, once we have so tiny, just the manufacturing error for the parallelism of the wave plate, okay, we can still, understand its effects through the optical transfer matrix. Okay. So this shows another one. Okay, it's another type of errors which forms the from the polarizing element itself. Okay, as I just said before. Okay, the polarizer is a type of polymer. Okay, it's made of polymer. It's a type of film. Okay, the film itself has certain just transmissions. Okay, transmissions. So these figures, okay, yes, we have just taken from the solar company. Okay, yes, you see the transmissions for the different, cannot become the perfect 100%. Okay, for the different wavelengths, they have a different transmission. To describe such kind of transmissions of a polarizer, they often use a parameter called the extinction ratio for such kind of to describe the performance of the polarizer. Okay, so here shows the changes of extinction ratio. Okay, so now we would like to show you how this changes. Okay, now let's see if we have the perfect, just the polarizer. Okay, gives the 100% of transmission. Okay, it means that the extinction ratio is 0. In this case, okay, the optical transfer matrix, okay, can take this, the ideal case. Okay, that is exactly the diffraction limited. Okay, optical transfer matrix. Okay, here we have this typical construction. But once, okay, we have certain, extinction ratio, it means that the polarity itself is not perfect. So if one overturns of the extinction ratio, as you see, for these elements, we can see we can easily observe a small cone for these elements, which indicate another type of the errors from the polarization element system. Okay, so here, let's say, in order to give just a description of the performance for the polarizing polarizer. Okay, here we use a cost function. This cost function can be defined as a variance of the polarization of the optical transfer matrix. Okay, here this is the subscript ABB represents some, the polarization optical transfer matrix with aberration, and the idea. Okay, the subscription of the idea represents the ideal case. Okay, with this perfect, elements. Okay, so here shows that once with the increase of the extinction ratio, okay, the cost function, okay, and become just reduced. Okay. So this is some of the errors from the polarizing elements. Okay. Now let's see another type of error. This type of error is related to the relative position between the imaging length and the polarizing element itself. Okay, so we call it the assembly error. The first assembly error is the rotational alignment error. As you see, during the experiment. Okay, so just let's say the axis, the fast axis or transmission axis. Okay, sometimes may not be perfectly aligned as we theoretically defined. Okay, for this reason, okay, it will introduce the rotational alignment error. So here shows this type the expressions for the generalized pupil matrix. Okay, and okay, now let's show you some results. So okay, let's say once again here, if the system itself has a quarter wave plate inserted, for the ideal case, without any rotational alignment error, it means that theta equal to 0, we have the ideal case for the optical transfer matrix. But once we have the rotational alignment error, as you see that this the optical transfer matrix has been changed. So here in these elements M12, M13, and M21 and M23, we can easily observe the other small cone structures for these elements. So once again, we can use this just cost function to describe the effect of this rotational alignment error. So here shows that when the rotational angle is 0, we have a perfect case. Okay, but once with the increase of this rotational angle, okay, this cost function can increase. Okay. Finally, I would like to introduce another example, another type of just assembly error, that is a tilt of the wavefront. During the experiments of the polarization related experiments, okay, we often intentionally introduce a tilt of wave plate in order to avoid the ghost image or double reflections from the surface of the wave plate itself. So we intentionally introduce the tilt. So this type of the tilt of the wave plate will also give the effect to the final stock image during the polarization imaging process. So as you see, once we introduce tilt, the optical path difference, okay, for the different locations will have a different than optical path difference from the wave plate. So in this way, we are able to write the generalized pupil matrix in this way. So here shows the result. Okay, now let's see, shows the result. When the tilt of the wave plate is pi/6, okay, radian. Okay, we can calculate the optical transfer matrix in this way. Okay. So if we continue to introduce the increase the tilt angle, okay, so here this phase term has been changed, okay, as you see in this figure. So if we still continue, now this phase term has become more irregular for these elements. Okay, so this is just this is the another parameters, okay, for the tilt of wave plate. Okay. So here is the conclusion of my today's talk. Okay, so today I have introduced the optical transfer matrix. Okay, from the optical transfer matrix as a frequency domain analysis of the optical of the polarization imaging system. Okay, we have given the definition for the generalized pupil matrix and introduced the different sources of errors in the polarization imaging system. Here just to show the different sources. Okay. that's the end of my talk. Thank you.
Thank you. Thank you very much for your nice report, for a nice speech. Please, questions. Please, participants of the conference, have you any questions?
Yes.
Yes, Professor Mohan, please.
Yes. My question is very simple. If we have ideal systems in one case, and with infinite pupil and so on, and in the second case, we have the system with aberrations. For example, astigmatism. We have some polarization distribution in the input of the system. We have we changed polarization distribution in the output of system with aberration?
Yes, the answer is yes. Okay, so first I should say that yes. Okay, I can
just a moment. What is the physical sense of this? You say here, this suit said here that no, it seems me you said that the X and Y component of the field has different conditions for the passing of systems. Is it true?
It's true. Yes, it's true. Because first, let me just continue my answer to your first question. Okay. So once, let's say even the system has a infinitely large aperture. Okay. So here we still have a certain kind of distortions of the wavefront. Okay, wavefront of this wavefront at the X pupil. So it's even we just take this pupil outside. Okay, because this pupil represents the finite apertures of the system. So the first answer to your question is that yes, even there is just an infinity of the larger just wavefront, we still have this type of the aberration. Okay, from the wavefront. Is the first question. The answer to your first question. Secondly, my answer to your second question is the following. Okay, this type of, let's say, I can answer you in this way. For the conventional imaging system, the lens itself, okay, serves as a modulation. The lens itself serves as a modulation of the wavefront. Okay, of the wavefront. But for the polarization related system, okay, any other polarizing element has already been inserted in the system. So in this way, not only the wavefront has already received not only the modulation of the lens, but also received the polarization modulation given by the polarizing element itself. So it means that when the light receives all of them, all this modulation. This is my answer to your second question.
Okay, may you return to the last slide before? Not before this slide, where you introduce the pupil matrix, generalized pupil matrix.
Okay.
Yeah. Yes. What is this W?
What is the W means that the W is the relative phase between the actual wavefront and the, let's say, the ideal Gaussian reference.
Just a moment. Yes. The wavefront may be introduced only for scalar wave. What do you mean the wavefront for vector field?
Okay, now let's say in this way. Okay, so first we just say that so far the conventional generalized pupil function, a pupil matrix itself is based on the scalar diffraction. So wavefront, as you said, that wavefront is just a scalar function. Okay, so here in the scalar functions, so we have the W is a relative phase between the actual wavefront and this spherical wavefront. this W. Okay, so once we select this reference, the spherical reference as our as our as our reference, spherical wavefront as our reference. Okay, for this spherical wavefront, it has a uniform state of polarization along all these spherical wavefront, because the light field is a electromagnetic field with its polarization. Okay, so this is I would say that this is just a uniform distribution. But once, let's say, there is any just aberrations of the introduced by system, okay, for the actual wavefront, the uniform state of polarization has already been changed. So for the different location, we may have a different state of polarization, as shown in the in the right figure. So for this reason, in order to take this type of polarization related changes into account, okay, here we just introduce another Jones matrix. This Jones matrix, okay, it can be considered to introduce the polarization related aberration. So that's the reason.
Thank you.
Thank you. Professor Sten Hanson, please.
Thanks, and thank you, Wang, for a very good presentation of your system. You have shown all the difficulties. Could you show one benefit, just one example where you can look through turbid media or anything like that? That would be very nice to see, Wei.
Yeah, so let's say in this way. So far, let's say I agree with your comment that so far the presentation today just is a deterministic polarization imaging system. Okay, but once just through this type of system, okay, once we introduce some kind of random birefringence in the system or something, okay, this type of optical transform matrix can also be extended to take the random birefringes into account. Okay, but here, let's say as I said that in this presentation, I only focused on the deterministic polarization imaging process, without touch the topic related to the stochastic imaging process.
Thank you, Wei. Thank you, Wei.
Thank you.
Thank you very much. Any questions? Oh, thank you once more for a nice speech. And now the next speaker, Professor Montemezzani, quantum-like approaches for robust photonics. Please.
Yes, thank you very much. I cannot share my presentation yet.
Okay, I just closed it. Is okay?
Yeah, should go.
Thank you.
1 second. Do you see?
Yes.
Okay, so I would like first to thank the organizer, Oleg, and all the organizers for the kind invitation, and especially for organizing this conference despite these still a bit adverse conditions. So I really hope that, I guess that's my fourth, if I count it well, correlation of this conference. And I really hope that the next one will be again in the nice city of Chernivtsi, so that we can meet all together again. So my talk will be a bit maybe different than most of those that you have heard until now. So it's actually about correlating a bit some stuff that you can do in quantum physics and in classical optics and photonics. Of course, this is not work that I do alone. So these are some of my co-workers, Charles and Hassan, our previous PhD student, Rim and Muhammad, present PhD student, Virginie is my colleague, and the work is going on in close collaboration with Sofia University in Bulgaria, with Anton Rangelov, Nikolai Vitanov, and also Kristina Christova, who is now at the Bulgarian Academy of Science, and part of the work also with Chaim Zukovsky in Israel. So let's give you my outline. So this is already all the outline. So the idea is that we try to remind a bit of what's happening in some coupled quantum system and see how, by analogy, you can use the same kind of approaches in classical optics, and specifically in guided wave optics, in nonlinear optics. And if time remains, I will also speak a little bit at the end on some aspect of polarization optics. So let's go on, and let me remind you something which is very well known. If you have a two-state system like this and you drive it in resonance with a coherent field, what will happen is that if this field stays on for a long time, you will get this so-called Rabi oscillation of the population between the two states. This is described by this kind of equation, which is found in the so-called rotating wave approximation. So it's a Schrödinger equation, and you have as important quantities here, you have the so-called state variables, which are here the population probability amplitude in the given state, and the coupling here, which is given by the Rabi frequency. And of course, the solution of this is such an oscillating behavior that you have seen before. Of course, this is something which is not limited only to quantum physics. There are many analogous systems in classical physics. Probably the most well-known one is the coupled pendulum. So I took from a nice web page this nice video that shows this alternating oscillation between two coupled pendulum. Of course, we are looking here at optics, and so let's see what are possible, among others, possible analogs in optics. So this is the two-state system I spoke about, and you can have something similar in coupled waveguides. These are two coupled waveguides with eventually varying distance between the waveguide. So in this case, the state variable is the mode amplitude in each of the waveguide, and the coupling is the evanescent coupling that you have between the two waveguides. If you look at nonlinear optics, we can have something quite similar. So this is, for instance, some frequency process. You have two input frequencies and one frequency you want to generate. And here you can reduce such a system to something similar to what it's upstairs there. The state variable will be the wave amplitude at the various frequency, and the coupling is given by the nonlinear optical coupling, or also coupling constant. And finally, for polarization, if we project our polarization either on a horizontal vertical basis or left right circular polarized basis, we get this state variable, and of course, as we all know, we can change polarization by various polarization transforming elements, for instance, wave plates. So I will go in that order, first waveguide and nonlinear optics, and at the end, polarization optics. Now let's start with waveguides. So you all know that if you have two neighboring waveguides, you can have coupling between them, which depends on various parameters. But if the waveguides are close enough, what you will see is such kind of things, that the light jumps if the waveguides are identical. Just from jumps from waveguide to the other and back. And this is a typical directional coupler. So you have a coupling length, which is here, which is related to this coupling constant. Of course, this coupling constant depends on many parameters, and which which can be seen here, of course, from the index contrast you have between core and cladding, and of course from the distance you have between the waveguides, and this is the parameter we will use to modulate this coupling constant in our case. And of course, it depends very much on wavelengths. And so this kind of elements are always highly dispersive. So that in general, either you know the wavelength at which you want to use the device, or you have some problems. And so there is a need for robust approaches that can accommodate, for instance, tunable or broadband sources or short pulse light sources. And as a side effect, you have also that such kind of elements will relax tolerance on the design. And this is all the idea of this robust elements, which can be inspired by some quantum physical effect. And the first one realizing this and providing an experimental demonstration of that was the group of Stefano Longhi in Milan that designed such kind of structure of 3 waveguides that reproduce essentially in waveguide optics this process that is known since about 30 years in quantum physics, which is called the stimulated Raman adiabatic passage. And I will give some detail on this effect in a moment. So the idea is that you can transfer light here, have a light passage in a very robust way, so independently of wave length, and also very robust with respect to the exact construction of this structure. So let's speak a bit more in detail about the stirrup, the stimulated Raman adiabatic passage. So this is already this waveguide implementation, like the one you have seen from Longhi. And the idea here is that you try to enter with the light here, and then you want to be as sure as possible the light will come out from this dirt waveguide, whatever your wavelength will be, whatever your temperature will be, and such kind of stuff. And the general idea is that this is an adiabatically evolving system that you actually are initially in your state, which is corresponding to the first waveguide here, but you are also in an adiabatic state that slowly evolves to end up here. And so basically you stay in one unique adiabatic state all during the propagation. And this is, as I said, analogous to such a system of 3 states, which is called the stirrup. So here the idea is that you have your population here, and you want to go here and be sure to get here. And this is done by coupling with 2 coherent fields, one which is called the pump field and the other Stokes field, with the corresponding Rabi frequency. Now, in order to be sure to get here, and also in a way not to get at all in this intermediate state, you have to use a trick, and the trick is to actually use a so-called counter-propagating sequence of this excitation, counterintuitive sequence, so that you actually apply the Stokes pulse before the pump. And you see that in time, the Stokes pulse will come first, and the pump pulse will come later. So this is counterintuitive because you are actually initially here. So the logical way to think would be that you couple first to state 2, you get here, and then you go down to 3. But this is not the best way to do it, and it was shown in quantum physics that's actually the other way around. So of course, if we translate this to our macroscopic world, this would correspond to this situation. So that's me at my home. And suppose I want to fly to London. My closest airport is Luxembourg. So usually I would say I take my car, go to Luxembourg, and then take the plane. But the stirrup would say that you should, in fact, the plane should start before I leave with my car to the airport. And despite of that, I get to my destination quite safely. And well. So of course, it doesn't work in real life. It would be maybe nice if you sleep too long in the morning, but it's working very well in quantum physics, and it's working very well in optics. So again, this summarized again. So on the left side you have the quantum system. Here are a couple more of states, so like 5 states, each coupled by a corresponding coherent field in resonance, and it's described as such a Schrödinger equation with the Hamiltonian here and the state variable as we saw. And the equivalent in optics is just to have a corresponding number of waveguides, each one coupled to the near neighbors, and you get the same kind of equation, the same kind of Hamiltonian, just with the coupling constant for the evanescent coupling between the waveguides. This is very difficult to implement experimentally, of course, if you have very many states, and this is very easy, as we will see in a moment. And you just have here the temporal dimension, which is in this system maps to the spatial dimension in this second system. So for most of the investigation we've been doing in this field, we can use some experimental approach where we use a nonlinear material here, strontium barium niobate, where under illumination we can change locally the refractive index. And so we can, with this spatialized modulator, then if you want record a certain structure of waveguides, and then we can check the light propagation in that structure by this probe light, which, as you see here, can be at 2 different wavelengths, so that we can check the robustness with respect to the wavelength, so the chromaticity of the stuff. And all is observed and in the back with the CCD camera. So the first investigation we did quite some time ago was on multi-state stirrups. So this many states, we went up to 11 states. This is a system already shown you before, and this is the corresponding system in optics. So it should be counterintuitive. What means here counterintuitive is that actually, if we inject the light here, you see that initially you have a large distance to the first, to the next waveguide here. This means that you have a very small coupling constant here, while you have already a much higher one between the output waveguide and the second last waveguide here. And you also see that this maximum coupling that you have where the distances are smallest, you get it first for the last 2 waveguides than for the first 2 waveguides. And so you have this kind of behavior, the Stokes coupling constant coming before the bump coupling constant. So let's see what this gives. So you can record first just input waveguide, you would get the light out, corresponding output, and then if you record all the others, so this is the calculated evolution, and this is what you get out in the red, so the output wave light correctly, and the same you get in the near infrared. Now the counterexample, of course, would be if we would have intuitive order, so that you would change a little bit the structure, and this is done here. You see that the calculated stuff is a mess now, and also what you get out is not at all this transfer So this confirms that this counterintuitive order is important. Then you can modify, of course, these things for other things, for instance, to getting beam splitting. This is 1-to-3 coupler, again very achromatic, due to the same effect that you follow a given adiabatic state. I pass on this, which is a bit of detail, and another approach you can consider now an isotropic waveguide where the index contrast is different for T and T M mode, and then you would get a nice transfer for one of the two, for instance, the T and for a TM you stay in the initial waveguide, and so you separate the polarization. And again, due to the fact that it is adiabatic, you can get a quite large spectral range where this polarization separation efficiency is good. Very recently, we looked at another case where we actually do not make any adiabatic evolution of the waveguides, but we exploit a dissipation in one of the waveguides. Now these are 3 parallel waveguides where the central one is dissipating, and this is equivalent to a quantum system where you have some losses, for instance, by spontaneous emission from the intermediate state here. And what you expect here, that's actually you can represent this input field here as a superposition of a so-called bright state, which is symmetric in the 2 external waveguides, and dark state, which is antisymmetric. It turns out that the dark state, the antisymmetric state, cannot couple to the central waveguide, and so it's not lossy and it's conserved till the end, while the other one is killed by the absorption in the central waveguide. So you have in this case you pay this extreme bandwidth by losing, in fact, half of the light, which is in the bright state. Here you see the cases for various parameters. You always get out with equal light in the first and the third waveguide, and the spectrum is flat, provided that you have enough absorption in the central waveguide. On the left side, it doesn't work because the coupling constant in that case is too small. So you need also a certain level of coupling constant. Okay, and finally, let me introduce another approach. So what we saw until now were always waveguides that were homogeneous on the longitudinal direction in terms of refractive index contrast. And if you abandon this condition, you can make also some analogy with another quantum effect, which is called the rapid adiabatic passage, which is effect which is or a process which is standardly used to make exact inversion of a state. So if we want to invert this state, one way is to start off resonance. For instance, you start a bit below resonance, so you have a detuning, and then in time you go across the resonance and you end up on the other side. So that you basically do this, and doing this, one can show that you can get sure to get all your population inverted. This is described by, again, such a Schrödinger equation with this Hamiltonian. And so what is important here are these diagonal elements which represent this detuning with respect to the resonance. That should change in time and go to 0 at a certain point. Now, what is the equivalent in waveguide? So the equivalent of the Rabi frequency we know already. It's the coupling constant. The equivalent of the frequency detuning here, it is detuning of the propagation constant. So of the beta, and this is actually related to the effective index of the waveguide and therefore also to the index contrast. And so you can modify, for instance, the index contrast along one of the waveguide, and you will get such a delta bit. And for instance, get this kind of behavior. So with resonance in the center, there where the coupling constant is the highest, and then the tuning on both sides. And this was implemented by our technique. So this is the expected calculation. This is just if we record only the input waveguide, and if you put the other one on the side, you see that the light jumps over to the other waveguide at burst wavelengths, which are about a bit more than 200 nanometers apart. If you don't do any detuning, so you expect actually that in one case you will return to the initial waveguide, in the other case you get something in between, and that's exactly what we also see. So tuning is absolutely crucial for this effect. So with that, I think I have finished the part on waveguides, and I will go on speaking a bit about nonlinear optics. So you all know that you need phase matching in nonlinear optics, because in a general case, the propagation velocity of the fundamental, and for instance, like here, the second harmonic is different, and this gives you to dephasing for dephasing for a second harmonic light that you have to compensate in some way. So there are essentially two major ways to compensate this, to achieve phase matching. One is to use the birefringence. So if a birefringence crystal, you can make such that for one polarization at one wavelength, you have the same speed like the other polarization at the other wavelength. Or alternatively, you can use quasi-phase matching, where you actually modulate your medium. You switch the sign of the nonlinearity periodically at the right distance, so that you build up this power like this, which is a bit less efficient than the birefringent phase matching, but in some cases it's easier to implement. So typically, quasi-phase matching is realized using periodic polling in some ferroelectric materials. So whatever you do, you will achieve this phase matching for a center wavelength or a set of wavelengths. But of course, if you depart from those wavelengths, you will not fulfill exactly phase matching. And this is a problem, of course, if you have very short pulse light, or if you have tunable light you want to address and so on. And this is a topic that has been studied quite a lot in the last 20 years or so, and there is a very nice review by Untitled that I give here about exactly adiabatic processes for frequency conversion. These are processes which are very closely related to what I said you until now. And if we focus here, you see that one approach is to make this quasi-phase matching, but to detune between negative and positive delta K. So this at the center position would be exact phase matching for your set of central wave lengths. for instance, this omega 1, omega 2, omega 3 that you have here. And then if you depart with one of those, you have to depart with the other, and then you would need another phase matching condition that you can find either before or after this center. And this is a way which is can ensure you to reach this other state, which in our case is the frequency omega 3, in a quite sure way, despite for your spectral content of your pump wave. If you look at this, it resembles very much what I showed before on the rapid adiabatic passage. And in fact, this chert quasi-phase matching is nothing else than rapid adiabatic passage implemented in nonlinear optics. So this is adiabatic approach. There is a lot of work on that. So before going to another approach that you may ask yourself, so you have three wave, why we speak about a two-state system. In fact, it's because we go to the so-called undepleted pump approximation. We can get rid of one of the equations. These are the standard coupled wave equation for nonlinear optics that some of you may be familiar with. These are some normalized ways of writing this quantity. The A is proportional to the square root of the photon flux. The D is also a bit modified with respect to the chi2. And this is the phase mismatch, which is close to 0. So we suppose that at the center wavelength we have phase matching. And then, of course, if you go to indepleted case, you can get rid of the last equation. And the other two end up being of that form, which is exactly this RAP form that we have seen before. The coupling between two states, one associated to omega 2, the other to omega 2. Okay, now adiabatic approaches are one way, but there is also another approach which is often used in quantum physics to make robust system, and this approach is called the composite pulse approach. And the idea is that in general you can map your final state, or your state. This is already for nonlinear optics, but it's the same in quantum physics, from the initial state by a so-called propagator. That's a matrix that map these two states. And now the idea is to cut down this propagator in pieces, so that to represent this matrix with several multiplications, several partial propagators, each one having a shorter length. And the sum of the length will give you the total length of your nonlinear material. And doing that, of course, you have a lot of parameters you can optimize. And the idea is to optimize this in such a way that you get to your target state at the end, even though your initial condition might be a bit departing from the central wavelengths, for instance, that were used to design the system. So the equivalence is between these composite control pulses in quantum physics and what we call a segmented nonlinear crystal in nonlinear optics. So and this is a general idea. So you have you want your bulk crystal, and then you choose lengths such that you get the optimum situation. In the first step, you can imagine that inside each one of these segments, you have the refringence phase matching at the center wavelength. And center wavelength means in this kind of diagram, phase mismatch is 0. So that's in the center here. And now if you depart either a wavelength or temperature or other things, you will automatically get a phase mismatch. So you will move away from zero. And the idea is that you get the optimum conversion, so close to 100% for a wide range of parameters. So essentially it means that we want to have this red region as big as possible in this case. And you see that what you have here is in the top, there's just one single crystal all along, and just by putting 4 or 6 segments, you already increase enormously this stable, robust region of conversion. So this is undepleted, and the undepleted regime we have here in the depleted. By extrapolation, you can look also at the depleted cases. Also there, it works relatively well. Okay. Now, of course, you don't need absolutely to have birefringent phase matching inside each of the segments. So you can imagine that each segment is already something where you have alternating domains for quasi phase matching. And then you have to switch each one of these segments with respect to the previous one. And what this ends up simply in imposing that you have at certain position 2 domains which looks in the same direction. These are the borders of the segments, and so you just need to find position to make this, if you want dedicated to defects at certain position to get this broadening of your conversion. And this was tested also experimentally by our colleague in Tel Aviv using magnesium oxide doped lithium niobate. And you see that you get much broader response for the case where you have this number of segments than if you have only the QPM design. This is for 100 femtosecond pulses, and you see the spectrum also of the second.
2 minutes. 2 minutes. I'm sorry. 2 minutes.
2 minutes. Okay, I will try to speed up. And also you see that here you get in terms of temperature, you get much more stable effect in that case. I will pass on this, which is another application on nonlinear optics, but for OPA, parametric amplification. Just very quickly on retarders. So you can apply the same thing for polarization, for polarizing elements like retarders, which are usually very, of course, very wavelength specific. Your propagator in that case is actually the Jones matrix. And so you basically now, if you want to make a composite propagator, you have to combine different Jones matrix. This has been done here, for instance, for the aim of getting broadband wave plates. Here is recent work we have done with respect to rotators. So rotator is an element that rotates polarization, whatever your input polarization direction here. And this is just a composite of 3 elements where actually just by putting a full wave plate in between, you can broaden highly the response. So the element works much better as a rotator than just by using 2 with half wave plates. As you all know, if you put 2 half wave plates under an angle, you get a rotator. And also the light is staying much more close to a linear state at the end. There is a small elliptical component that is much better than in the case of 2 wave plates. So let me conclude. So I hope I could convince you that there are nice relationship between stuff that are done in quantum physics and stuff that you can do in optics for various kind of optical elements. I'll show you some examples for related to integrated optics, nonlinear optics, and very quickly on polarization optics. These are some papers that we have published over the last few years on such kind of things. And let me thank you all for your attention. Thank you very much.
Thank you very much.
Questions.
Thank you very much for your nice speech. Now, please, questions. Dear participants, your questions? There are no questions. Thank you very much again. And now we will, thank you, and we will invite our next speaker, Professor Fainman, Nanophotonics Technology for Information Systems. Thank you, please.
Thank you very much for the introduction and the invitation to make this presentation on nanophotonics technologies and applications in information systems. Okay, so I'm delighted to give this talk, and I'll start from kind of evolutionary presentation of how optics and electronics developed during the past 100 years. So we all know when the electronics evolved in the early 1900s, we used vacuum tubes replaced by transistors, and then today we are having this microprocessor. So the progress and the advances are primarily due to simple one term, lithography. We learned how to densely create this electronic, very complicated structures that perform different information processing functions. Now, in optics, we also started from telescope, built cameras. Then in late 90s, 1980s, we started to use lithography to make diffractive optical elements. At the time, the resolution wasn't that great, so we couldn't make too much progress in this direction. But today, lithography reaches deeply sub-wavelength features on the scale of tens of nanometers, and we can actually re-evaluate how we deal with materials in photonics. So that's more or less the theme of my presentation. And history here shows that it always develops in a spiral. We revisit the same things 20, 30 years later. Sometimes we invent a new buzzword and call it a new field, but it's actually an evolution. Same old story with some modifications in theory, where we need to take into consideration certain assumptions that are not valid anymore, like nanoscale materials versus microscale materials, where diffraction is sufficient. In nanoscale materials, composites, we need to go back to Maxwell equations. So that's the whole difference. And today, this field is called metamaterials, but it has a long history into 1960s, when Adolf Lohmann was the first to talk about computer holograms. Okay, so everything was synthesized in the computer. So here is an outline, a brief outline of what I'm going to talk about. I already talked about some historical overview on different nanostructured surfaces and resonant passive nanostructure. Then I will talk a little bit about nonlinear optical metasurfaces and applications. One application showing 1 gigahertz spatial light modulators, and I will mention what the implication of such fast spatial light modulator could be. And then I will go into active light emitting nanostructures. And I call them metasurfaces just for the sake of being compassionate to the inventors of this buzzword. And that basically will lead me into the future research direction where we can start thinking in optics about the same paradigm as in radio frequencies phased antenna array, but they're active. It's not the beamforming that we used to call in diffractive optics. So that's a distinction I'd like to stress. So I'll start from a very generic description that if I have atomic scale subsystems separated at distances larger than the wavelengths of light, we all know this is leading to micro-optics. Diffractive optical elements falls into this category because we barely reach scale of wavelengths of light. So, for example, a grating would fall into this category. Now, what happens when I take these atomic subsystems and bring them closer to each other? We all know that they will start being electromagnetically coupled or near atomic scale subsystems. We call them in that case, in microwaves in 50s, they were called artificial dielectrics. We call them composite, and we can also make some resonance structure like photonic band gaps. Now, the most interesting question, what will happen if we now look at what we are able to create today, and there is a lot of open opportunities in the future, is when we combine the local atomic scale subsystems where the material themselves have some internal interactions. For example, just brute force example is Raman gain in nonlinear optics, or some superlattices, quantum wires, dots, etc. By the way, these structures also can combine the electronic and optical properties, for example, electrically pumped semiconductor lasers, where you inject current and produce photons. Now, what happens when on top of it, you start looking at electromagnetic interactions between neighboring lasers on nanoscale? Okay, so that's something that I will try to address at the end of the. So this work we've done probably 30 plus years ago, then we looked at work from Weiner back in 1912, who analyzed formed birefringers in electrostatic. And it's very simple. If you have periodic structure on deeply sub-wavelength scale, this capital lambda is much less than the wavelengths of light, you end up breaking the boundary condition for TE and TM field, and you create artificial birefringence. So TE is continuous on the tangential component is continuous, the normal component electrical displacement is continuous. So clearly TM, effectively the TM mode will sit in the air, and the TE mode will be averagely sitting between the air and the high density dielectric blue boxes. So at the end, if you estimate the delta M for between the index that TE and TM field sees, you end up with a huge birefringence in comparison to delta N. The largest birefringent crystal we can get is delta N of 0.2. Here you can easily reach delta phi in radians of pi. So depending on duty cycle, you get different form birefringence and so on and so forth. So you can optimize, play with it. But what is it good for? We did some work in the past using form birefringence to make polarization selective elements, made resonant polarization optics, drag structure with form birefringence structure imposed on it. So the two stop bands are shifted significantly. So it reflects TE and transmits TL. You could also design a photonic crystal, in this case 2D photonic crystal, and you clearly see a huge stop band for the TE field. Now, if you make few structures to make it up a device, you can easily create a very effective resonant device, such as a Fabry-Perot modulator. So all this was done back in 1995-97 timeframe, and then later we looked at the same structure again and found that actually by writing these gratings, wavelength gratings, graphically we can encode phase for incoming polarized beam. It can be space variant as form or space variant, and can be continuous and pixelated. So this is an example of a pixelated. So every pixel is the grating is oriented under different angle, and as you come in with linearly polarized light, you will experience a different phase delay. So you modulate your wavefront, the phase of your plane wave incident on such structure. But interestingly, you can write these lines continuously, and this is nothing else but you literally control the orientation of the effective optic axis of this birefringent crystal. So in this case, you can easily design a structure using this expression and create that linear depolarized, say horizontally light will result in radially polarized light, or you could design azimuthal polarization at the output. Why is it good? Some people showed that with this radial polarization, you get a donut-shaped far field, which improves the resolution. So now I'd like to move from the passives to actives, and the first active will be just nonlinear effects in optical metamaterials, and then we'll talk on the actives that emit. So for the beginning, I'd like to talk about the second order nonlinearities in silicon nitride, which we studied for quite a few years, back maybe almost 20 years ago. We for the first time measured the M2 to now today what we are doing is measuring using this Maker's fringe setup that is nothing else measuring Fresnel coefficients in a thin film by inputting a pump and generating the second harmonic. The film is thin, so we don't worry about phase matching condition. It's much thinner than the coherence lengths. And in this case, we rotate the orientation of the incident polarization and measure the polarization state of the output second harmonic. And from this, today is everything automated software. With the software, we extract the tensor component of the chi2 and chi3 coefficient. So to make sure that we measure from bulk, we made different thicknesses and measured the second harmonic as a function of thickness should scale quadratically as shown here. So yeah, sure, it's from the bulk and not from the interfaces. So in this study, what we did, we prepared 3 samples of silicon nitride with different content or concentration of silicon, sample 1, 2, 3, with more silicon in sample 3 than in sample 1. And the refractive index, by increasing concentration of silicon, refractive index grows, and we know that as the linear susceptibility grows, the chi3 will grow too. So that's basic from the textbook. And we did some measurements of these 3 samples. And on the left-hand side of the slide, you can see that for index 1.92 and 225, we measured as grown film. We measured a small but appreciable chi2 on the order of 2, 5, and 8 picometer per volt. This was done with 800 nanometer femtosecond laser pulses, generating 400 nanometer second harmonic. And the second trick we did was put electrodes around this silicon-rich nitride film. And by applying external voltage, the whole idea was to use DC-induced Pockels effect. In other words, it has also every material has chi3. So in addition to chi2, what we wanted is to apply DC field and couple the chi3 times DC field to create an effective chi2 that will be larger. And that's what we measured here. So if the polarity of the voltage is, the dipole is, induced dipole is collinear with the inherent dipole of the chi2, it will grow. And if we apply field in the opposite direction, it drops to 0 and then grows due to chi3. So we clearly showed that we can increase the effective chi2 to values of about 22 picometer per volt. So that's appreciable value. And I forgot to mention why silicon-rich nitride. The only reason is that today trend of nanophotonics is towards CMOS manufacturing. Now, silicon nitride is one of the CMOS compatible materials. There are 32 materials. So we want to use these materials as opposed to crystals, which is not trivial to integrate with CMOS process. So that's the major reason why we are looking into this kind of composites. So the other idea we got from this DC-induced Pockels effect can be built in the material, built-in electric field. And the answer is, of course, yes, otherwise I wouldn't talk about it. Took a layer of silicon dioxide that has a tendency to have positive and aluminum oxide that provides negative surface charges, and made a sandwich with amorphous silicon. So clearly, holes will get attracted to aluminum, electrons will get attracted to the silicon dioxide layer. Consequently, there will be developed a charge separation which will be held by a DC electric field. And this internal DC electric field will couple into the chi3 coefficient, producing an effective chi2. So that's the whole idea. These are a couple of simulations showing that electrics on the interfaces of amorphous silicon is zero field as expected, but this positive negative, you end up with reasonably high internal electric field, order of 10 to 5 volts per second. Breakdown voltage usually is in the range of 10 to the 8 volts per meter. So this is like 1 order of magnitude below the breakdown. So that's appreciable field. So that's what we did. And from measuring the with the same makers, fringe makers system, that chi CCZ was 1 and 2 periods. We did 2 periods as well. Estimate around this approach. If we do annealing, we improve a little bit, not a whole lot, but for annealing at 400 degrees, which helps to develop more higher density of charges on the interfaces. And we can hit chi2 ZZZ effective at around 8 picometer per volt. And we said, okay, can we play another game? So what other games can we play? Create internal. If you consider taking amorphous silicon with work function Fermi level at 467 eV, if you put on one side metal with smaller work function at 4 eV of aluminum, and on the other interface nickel with 5 eV work function, we create internal field as shown here again. And the same scale, about 2.5 times 10 to the 5th volts per centimeter. So by using this internal DC field through the chi3 coefficient, we end up with chi2 effective. Call it an effective, and this details were in this paper. And I don't think here anything I didn't say before, just SEM fabricated structure, and bring up the point that these metal contacts now do patterning. So that's what we actually did. Here is a summary of what we used nickel aluminum, and we also replaced nickel by platinum. So you get a little bit enhancement in the chi2 coefficient. Just for comparison, lithium niobate has around 36 picometer per volt, so it's not as good as lithium niobate, but that's the punchline. So as I said, we deal with metals, so it's very easy to make electrodes. So you can make any structure where you create an internal chi2 space variant in a space variant fashion, where you put metal, you get it. Where you don't have metal, you don't get it. So that's we did a study just to check if the concept is correct. We did a study of putting a grating as one of the electrodes, and then we anticipate that we will get the second harmonic generated in the only in the orders of the grating. That's what we actually observed. So, of course, we can also on top of it, we can add external DC field since we have the electrodes, and that's what we measured here, that we can enhance the second harmonic power by about an order of magnitude by applying external DC voltage. In other words, further enhancing the internal DC field. Now, what all this good for? That's literally a question we asked ourselves. Why would we care nonlinear optical materials? So one kind of obvious answer is telecom applications, where people today are pretty much building transceivers on a silicon photonic chip. So having a Pocales-like modulator instead of reverse bias PN junction, PIN junction, as a modulator, which is lossy, would be advantageous. So silicon nitride could become a modulator. But modulator in university, we are not set to do products. So we ask ourselves, what else could we do that would benefit from the high speed of the Pocales modulation? So we were thinking of 2D SLM, and the question was, why would I care about high-speed SLM? And the reason is that a lot of activity recently has been paid to use silicon photonics in neuromorphic computing, for example. Now, the catch is in free space, we have 3D connectivity. In silicon photonics is guided wave structure, so we cut one dimension, we are in 2D, so you end up with 2D connectivity, and then the number of processing nodes will be limited, and this will limit scalability of the approach for this type of applications. So the question is, can we construct high-speed SLM processing free space or evanescent modes? It doesn't have to be a bulky free space systems, such as I remember building when I was a student. But, today we are looking at very compact 3D realizations of 3D connectivity using either evanescent modes or co-packaging with between optics and other electronic structures. So the question is how to build a 2D SLM, and this is a summary of the state-of-the-art sort of. There are types: digital DMD. This is an instrument. If you go to movie theater, the projection devices now are using DMD. They changed the name DLP, digital light wave processor, but these are MEMS mirrors. This is the second one is pneumatic liquid crystal. Give and take all the television, the flat TV we have at home are using that device. And there was ferroelectric liquid crystal on silicon that is lossy but much faster. So still, the time response of DMD is around 14 microsecond response time of individual mirror. Pneumatic liquid crystal is worse, it's in the tens of milliseconds, and ferroelectric gets into the microsecond scale, but nothing to be able to operate at gigahertz. So recently there were a couple of developments, but they are still in the kilohertz scale because they use some of the mechanical motion. So this is kind of abstract of our paper on the programmable plasmonic phase modulation. free-space wavefronts at gigahertz rates, and I'll talk about it a couple of words. So the whole idea is to construct a pixelated array of electrodes, and the principle is literally we use the internal reflection silicon prism here. The operation is said and we sputter a thin layer of metal and then nonlinear material, and on top of the nonlinear material we put the pattern electrodes. So what happens? The evanescent tail mode here excites the surface plasmon polariton, but because of this patch, it acts as a patch antenna or a small resonator. So in this area, depending on the voltage in between applied to the nonlinear material, we can change the phase of the reflected beam in this pixel versus reflected beam from that pixel, and so on. Of course, the size of the electrode has to be sufficiently long to achieve appreciable phase modulation. But the patch resonant structure has a Q of about 10, and the effective index of SPP for SPP is relatively high, so everything is favorably scaling for getting this phase modulation. So how did we construct it? It's a silicon prism, as I explained. It's 48 nanometer silver, surface plasmon waves. We take sapphire wafer, is 4x4 electrodes, and all these guys are mechanically pressed together and inserted into this characterization setup, which is nothing else but a Mach Zehnder. And we measured the phase as a function of applied voltage. And the phase modulated the voltage, we change in time at 1 gigahertz. So here are some experimental results clearly showing field modulated 1 gigahertz. And then we also used it, of course, not at 1 gigahertz. Photonics to do it. So this experiment was in DC, but we wanted to see how much cross interference resonant patches of them. And you clearly see here that when you activate all of them, they're all bright. And when we want to put some propaganda for the University of California, San Diego, you can also see it UCSD here when we change the voltages. So that's great. It worked nicely. I think I'm wrap up pretty soon. So I'll talk a little bit on what I want to light structures and meta surfaces. First, take a look at the nanolasers and then try to convince you that it's very exciting to go into programmable apertures with nanolasers. So this slide is actually a summary of evolution, what we have seen in laser technology. We started from the maser, so it's literally a microwave. That was a 3D cavity. Then we had the Ruby laser. Old enough probably remembers the Ruby laser. I was getting it when I was undergrad students. was a great invention, but it used only 1D cavity, the Fabry-Perot cavity. Then semiconductor lasers became available, and they were again edge-emitting lasers, plus DBRs, but there's still the cavity is not a true three-dimensional cavity. So this is a pixel, still 2D Fabry-Perot cavity. So can we make a 3D cavity like for microwave, but for optical waves? Now, the problem is, of course, have to confine the mode in a small volume, not to get too many modes, because if we have huge amount of modes, I will talk about it later, it's not really useful for many applications of lasers. Multi-mode emission is not advantageous for many applications. So what do we want? Why do we want it? Small mode volume, large beta. I'll talk about beta in a minute. Beta is a spontaneous emission factor, which is mode power funneled into the lasing mode, divided by power funneled into all the other modes. So multi-mode operation beta is on the order of 10⁻⁵. All commercial lasers 10⁻⁵, 10⁻⁴. For the lasers, if I have only one mode that the cavity supports, my beta will be 1. And why do I care about beta? We'll talk about it in a minute. And of course, smaller volume, faster relaxation time, so you can modulate laser at higher rate. Here is an example of some work we did 10 years ago. Was to create a laser that operates at room temperature, is sub-wavelength size and T, and isolated from. So to create such a laser, we have this gain media. This is the bluish is the electric to reduce the loss into the metal cover. So it's a 3D metal cavity with a tiny hole at the bottom to pump and to emit light from the laser. And clearly you can see here that we have a laser because light-light curve shows a king. And this is spectral evolution, and this is the spatial mode. I think I'm going to skip few slides explaining the principle of our designs and go into the beta 1 layer. And the whole idea is to use a coaxial resonator. Know that in TV, our frequency is 200 megahertz, and the transmission line is on the scale of half an inch diameter. What happens is that coaxial cable always supports TEM-like mode. So we took the advantage of coaxial and made a design of the structure such that the emission mode across the gain spectrum of the gain media, this red, is only one mode. The degenerate modes are pushed away, okay? So, out of the spectral gain window. So now we clearly have beta equal 1. There is no king in the light-light curve. And why beta is important is explained here. If you look at rate equations for amplitude of the magnetic emitted wave, carriers, and the phase of the you end up, usually people kill this spontaneous emission factor with the beta. Now, for the large lasers, beta very important. Beta is not important. For small lasers, beta is very important because it's a 1. It's not 10⁻⁵. So what's the significance of beta? When beta equals 0, you have, and you measure fluctuations in intensity of the laser when you turn on the current, say, step function, you end up with long oscillation time, overshoot. When beta goes to 1, the damping is very fast. So you can intuitively understand that when damping is fast, if I want to do phase locking of two lasers next to each other with large beta, I will be more successful than with small beta because of this independent relaxation of the two different entities. So the damping is very critical for in-phase locking of. So we conducted quite a comprehensive study, theoretic, on stability of in-phase and out-phase locking, shown here on this diagram. And you can clearly see this is the coupling amplitude between two nanolasers and this phase. So depending on the amplitude, this is strong coupling regime. It's difficult to get there. But even in decoupling, you can clearly see beta is a parameter. So then when beta is 1, all this red region in phase locking is huge. As beta goes to 0, you can clearly see this curve pushes the stability region to a much smaller stability area for in-phase locking, and the same applies to out-of-phase, the blue region, out-of-phase locking. So with that, I'd like to bring up one more point that depending on beta, this emission factor, we can also change the relative phase between the two adjacent lasers by pumping them not equally. So here is the horizontal axis is beta, the vertical phase tuning range. So you can clearly see that from beta around 0.05 or so, you can achieve a pi phase shift by tuning the relative pump by 20% above threshold. And for commercial lasers, 10-5, 10-3, the phase tuning range is about 0.1 pi. So you can't tune more than 0.1 of pi. Now, why I want to tune by pi? Because now I can program different lasers in the array and create far field, whatever I want, but I will need 2 pi phase modulation. To get 2 pi, we need to be able to switch between in phase to out of phase locking and then tune the modulation. This is not a trivial problem, but it's interesting to think about it. So why phase locking array is important? Knows this LiDAR problem that everybody cars, UAVs. But so far, what people have done is use laser. And it's not the same as.
I'm sorry, 2 minutes, please.
I'm done. You can have back the 2 minutes. So this is conclusions and summary of what I showed you. I'm going to read through it. I will go to acknowledgements. It's of course all done by lots of grad students, and funding is appreciated from different funding agencies, and I'll use a minute for propaganda. We recently, in academia, we do research, and sometimes the education is not always prime job, which is wrong. So we try to correct it. And during pandemic, this was a great approach. We developed an integrated photonic education kit in silicon, and you can see this gadget is very small, electrical wire, optical fibers array out, has in it all different devices, and it is interfaced to a computer, and we are working on making it available through internet to conduct the experiments in the lab remotely. So this way, pandemic doesn't affect us as much. So that's literally end of my presentation. Thank you very much for your attention.
Thank you very much for a nice speech, deep speech. Please, questions. Please, Professor Mohan.
I have practical questions. What you can say about the maximal power in your programmable SLM and in the space variant Biot converter? Can you say something?
Yeah, the loss is less than 3 dB. Of course, plasmonics is always lossy, but we didn't see more than 3 dB loss, which is tolerable. At 1 gigahertz, many things are tolerable. Now, regarding the, I didn't quite follow the second part of the question on the nonlinear. What was?
Space variant Biot converter of polarization linear to azimuthal and radial.
Okay. Yeah. So what was the question?
What is the maximal power?
Well, this depends on your material. It's passive, right? I just do etching in the surface of the material.
Approximately, approximately. Watts, milliwatts?
I don't know about watts, but I think watts per centimeter is watts per centimeter square should be easy to achieve.
Mm-hmm. Thank you. Okay.
Other questions? Professor Fainman, thank you very much for your very nice report, for your participation in our conference. Thank you again.
Thank you. Thank you for the invitation.
Thank you. The next speaker will be Professor Steen Hanson from Denmark. Optimum signal processing, having optics and electronics working side by side.
You can hear me now? Good. Thank you for the invitation to the programming committee. I must say that this is a rather easy presentation because it's more engineering, but nevertheless, I think it could be interesting for you. So I will cite previous work with Wang, Scotland, who is here right now, Mitsuo Takeda from Japan, Hal Yura from Aerospace Corporation in the United States, and my co-worker Michael Linde Jacobsen from Denmark. The overview of my talk is I will talk about the general idea and the basic considerations, and then I'll give some important examples calling for electronic processing, which are center of line, that means position detection, its fringe pattern, especially finding the frequency or the phase to be determined, and then the cross correlation peak center of detection. if you have an optical system, you need to do some processing, and these are three of the most important systems you can come up with. And then I'll talk about zero crossings, and I'll end up with the conclusion. So I'll treat as an example a spatial dependency, but this could just as well be a time dependency, treated in the same way as I do right now. And therefore, I excuse for this contribution, which might be slightly offset from the theme of the program. The basic concept is, if we have fringe pattern, for instance, and we have not additive noise, we have signal-dependent noise. That means where the intensity is high, we have a lot of noise. Where the intensity is low, we have very little noise. That means, as it's shown in the equation, that the signal itself, S of x, is consistent of the S0 of x, which is the signal without noise, and then we have the noise contribution 1 plus n of x. If we intend to find the frequency, what we would do is usually make a Fourier transform and then make a Fourier transform absolutely square, and then find a peak, use a peak detection to find the peak. But that means that we'll focus on the signal where the noise is high, but we, as I can see it here, should focus on positions where the signal, the total signal is low, because that's where we have very little noise. So we should put emphasis on the dark part of the signal itself. So we have the intensity, which is from the bins in a detector, or it's a time-dependent signal. And if we take logarithm to the signal itself, we have the signal on top, I of x, is the no noise signal, I0 of x, plus 1 plus n of x. And we take the logarithm to this signal, we see that we split it up in log I0 of x, which is really not stochastic, and the logarithms are 1 plus n of x. The stochastical part is logarithm of 1 plus n of x. And now the multiplicative noise is converted into additive noise. So we have the stochastic part in the upper part, which is the intensity itself. And in the lower part, when we have used the logarithm, we have transformed the stochastic part into the noise itself, n of x, which is now additive. So the multiplicative noise is converted into additive noise. So the PDF for the signal in 1 bit is, according to Goodman, the probability of the integrated power in 1 bit is m, that is the number of speckles in one of the bins. So if m is 1, it means that the speckles have the same size, or maybe they're larger than the bins or the pixels. And if m is large, we average in each bin or in each pixel over very many speckles. We have the average value, that's the average value here. My angular brackets, they indicate averaging. It could be ensemble average and time averaging. And we have m, which is again the number of speckles in 1 bin, and w, that's the stochastic variable. So for each bin, we have the probability distribution of a certain reading w, which is given by m, and is given by the average value of w. That's the PDF, probability distribution function. Now we assume, as before, that the reading in 1 bin is the average reading times 1 plus n, where n is the stochastic variable. So we change the variables because we have the stochastic variable w, and we have a stochastic variable n, and we change the stochastic variables from a probability distribution of w from up here into a probability distribution of the noise, the additive noise here. And we get this expression, which is rather easy to find. And if we look at it For instance, we have the probability of certain reading in a bin, which is for m equal to 2. That means we have 2 speckles in each bin. Looks like this. Of course, if m was equal to 1, we will have the ordinary negative exponential distribution. And we see how the distribution looks for the noise part. And we see that we have something which looks a little like this. It starts from -1 because we need m to be larger than -1. And again, if m was equal to 2, we'll have a negative exponential distribution. So we can calculate all the first order moments first for the signal itself, and its 0 is independent of the number of speckles in the bin, whereas for the average of log 1 plus n, we'll get something which goes from negative up to 0 if m is rather big. So here we have 15 speckles in a bin, and down here we have just 1 speckles in a bin. And again, we can get the second order moment, and we can get the second order moment for log 1 plus n squared, and eventually we can come up with the variance. They look very similar, but the variance for the logarithm transformation is a little larger than the variance for the signal itself before we take the logarithm. So we have the standard deviation for the direct one, which is the orange part, and we have the standard deviations when you take the logarithm to the signal, which becomes a little larger. So we can calculate exactly what is the variance for the original signal, which is proportional to, or is given exactly to 1 over m, where m is the average number of speckles in a bin, whereas the variance for log n plus 1 becomes polygamma of 1 comma m. So we have an exact number for this part. Especially we can get the average value of the ensemble average of log 1 plus n, that is n is the stochastic variable, which is a noise, becomes Euler gamma, whereas the second order moment of log 1 plus n becomes Euler gamma squared plus pi squared divided by 6. So the standard deviation is pi divided by square root of 6, which is 1.3. Whereas before we make any logarithm transformation, we have the average value of the number is 0, and we have the variance being 1. That means the standard deviation becomes 1. Still, the standard deviation, when we do the logarithm, becomes a little larger than before. But as I'll show a little later, we can still benefit from doing the logarithm transformation. And that's because the sharpness of the peak we're going to determine the position of becomes much sharper. Therefore, we can benefit from the logarithm of the signal. For instance, if we want to determine the center of a projected line, that's done here with triangulation. We send in a beam onto the target, and we image the target onto an image plane. And if we move the target backwards, we'll see that the image will move here. So at the end of the day, we need to find the position of the line or the center of the line. And you can do the same with having a set of lines across the object and thereby get the topography of the object. So if we had no noise, we would see that the center or the intensity distribution across the line would be like this. Unfortunately, or I could say that's how life is, that we get the multiplicative noise, and we see that this could be like this, where we have a lot of noise, where the intensity is high, and a little less noise at the wings of the distribution. So we tried 3 different ways of doing it. First, a Gaussian fitting over 20 pixels across the line here. That would be the standard method of doing it. Then we did a quadratic fitting over 20 pixels of the logarithm to the total intensity, like log 1 plus s of x. S1 is just an arbitrary number I add, or we could add 0.1. That's in order to avoid any numerical instability. And we calculate this. We calculate the standard deviation of these three fitting methods with varying degree of speckle noise. That means that the speckle averaging due to final pixel size. So this is the result when we do it 40,000 times. So the noise level going from 0 to 1, almost 1. I stop here at 0.7. And we have the standard procedure where the standard deviation, for instance, if we have a noise level of 0.5 here, the noise would be something like 0.28, the standard deviation in pixels. But if we do the logarithmic transformation before we find the peak of the center of the line, we see that for 0.5, we get something 0.2. That means we have a 20% increase in accuracy, and we have no bias effect. It's done by simulations, but I should also add, and that has to be franked in this way, that I have no additive Gaussian noise. Because if I have additive Gaussian noise, the situation might be different. So the another optical system we want to analyze, that is, we want to detect the frequency of a speckle pattern. I'm sorry, in a fringe pattern. That could be done in different ways instead, in order to get the topography of an object, or in time to have, for instance, an OCT system to find the frequency here. So this is one example that we have a fringe pattern without noise. We put or add the signal-dependent noise, and the signal could look like this. So we have 4 different schemes that we have employed. First, we take the Fourier transform of this signal here, and we find the peak. That's the ordinary way to find the frequency. But I also do it with taking the spectrum of log 1 plus the signal, or the spectrum of 0.1 plus the signal, or log at a very small number. Again, these numbers are arbitrary numbers that I have put in just to see how they change the outcome. Again, I do it with a varying degree of speckle noise. That means that speckle average size. So this is the fringe pattern, and this is log to the fringe pattern. Again, we see maybe the noise is lower, but here we have very fine, well-defined minima, which make it easier for us, I assume, to find the correct frequency. Again, multiplicative noise here is converted into additive noise here. We can find the correlation function of, this is rather simple, of 1 plus cosine omega delta x divided by 8 in this case. And we find the correlation function not of the signal itself. We know the correlation function for this signal, but we find the correlation function from log to the signal plus times log to the signal displaced distance delta x. And we see we have a DC value, and then we have a modulation. And the modulation, these are the correlation functions, the numbers in front of the correlation function, the strength of the correlation functions after doing the logarithmic transformation. We see that we have a modulation depth which is increased due to taking the logarithm of the signal. So to our simulations, which are 10,000 times simulations, and we have the speckle size as divided by the pixel size. That means here the speckles are equal to the pixel size. Here the speckles are much smaller than the pixel size. This is the standard deviation as a function of the noise or the speckle size divided by the pixel size. For what we would usually do, that means the Fourier transform the signal itself, find the peak, and we'll get a standard deviation here in 1,000th of a pixel. That means up here, when the speckles are equal to the bin size, we have 0.07 standard deviation. But if we do the logarithm, here it's with this additive, arbitrarily induced parameter 1, 0.1, 0.01. Again, they were introduced in order to have numerical stability. We see that we really can reduce the standard deviation. The standard deviation goes with an increase in 6 times in the accuracy, just merely by taking the logarithm to the signal. I might add that I found one example of doing the same thing here, but with a maximum likelihood estimation. And I should say maximum likelihood estimation is the best way to do this, but it's very cumbersome and it takes a lot of time and effort to find the right value. But I think it was Jonathan who made this maximum likelihood estimation, and he came up exactly with a 6 times increase in accuracy. So it seems like this, I should say, poor man's approach is getting the same result as a full-blown maximum likelihood estimation procedure. So I assume this added parameter, that's a 0.1, 0.01, should probably be adjusted if we have some additive noise present in the original signal. The more additive noise we have, the larger this parameter should probably be in order to still have numerical stability. So we go to cross correlation. I have found the center of a peak. I have found the center frequency of a fringe pattern. And I told you that I would do the same with cross correlation of 2 signals and take the logarithm of the 2 signals. But unfortunately, that didn't give any increase in the accuracy at all. But previously, Wang, who is present here today, and Mitsuo Takeda and Miyamoto, we did some experiments where instead of looking at the signal and cross-correlating 2 signals, we looked at the singularities. In the case of this paper here, we took an ordinary intensity image and we transformed it into a complex value signal by applying a Hilbert transform. Maybe I think it was a Riesz transform. And now we had the complex signal from the intensity image, and we could find the singularity points with sub-pixel accuracy in the complex system signal. And this was, of course, done in both the original imagery and in the imagery that has undergone transformation. And based on tracking the 2 recordings, that means tracking the displacement of the singularities, which we could recognize based on their ellipticity and charge, we could find the displacement of between the 2 patterns with a very high, incredible high resolution. So Wang did some experiments with fugu fish in this case, and here we see how the different singularities are paired, and that means you can track the entire movement of this fish in this case, again with a very high precision. So the last part of my presentation is to find level crossings for an arbitrary stochastical process. Find an analytical expression for the level crossings. And for measuring schemes, we could make very simple processing schemes if it's allowed just to look at the level crossings and track the level crossings for a signal. So this is just an ordinary system, and we would find the number of level crossings per distance or per time, whatever you choose, and you have a number of level crossings. And for our goal is to find analytical expression for the level crossings for an arbitrary distribution. And with arbitrary distribution, I mean that we got to have a probability distribution function for the signal with which we are going to find the level crossings. We also have spectral distribution. But what we know is that the level crossings for a Gaussian distribution is known. And what we do is that we kind of take the level crossings for a Gaussian distribution, which we know, and we squeeze or vertically magnify the signal to fit the desired distribution and let the crossing points follow the transformation. So now the crossing points have got new and known values, while the number of crossings attain the original value. We start out with a very excellent paper by Rice in the late 1940s, where he had a signal and its first derivative, and they are uncorrelated. So that means the ensemble average of y of t times y of t prime is equal to 0, where we have the ensemble average. Two parameters that are uncorrelated and both have Gaussian probability distribution functions are independent. If the PDF of a signal is Gaussian, so will the PDF for the first derivative be Gaussian, as it is derived from the difference between two Gaussians. And then Rice has found an expression for the number of level crossings for a signal with a given spectral distribution and a given variance in the signal, and the number of crossings is given by the second order moment of the spectral distribution. This is the basis for our investigations. But we should like to find a level factor for our PDF for the in this case, the spectral factor and a level factor due to the compound PDF for the signal and its first derivative separates. So they are independent. Our approach is to transform the given signal y of t, that's the signal with which we should like to find the number of level crossing. We will transform it into a signal x of t with a Gaussian PDF and a unit variance. That means we have the probability distribution for the Gaussian, and we have the probability distribution for the first derivative of the Gaussian. And we should now find this combined probability distribution for the signal we are investigating, the signal in which we are going to find the level crossings. So we need the Jacobian. Here we have the Jacobian. And in order to proceed, we need to have the CDF cumulative distribution function for the Gaussian, and we need the cumulative distribution for the signal under investigation. And if we find the CDF for the Gaussian and we insert that here, we get the cumulative distribution function for the arbitrary function. And now we are almost home because we can put it into our expression, and we find that the number of level crossings at a certain level y0 is equal to, we need the CDF for our signal under investigation. And we of course need the square root of the variance for the first derivative of the signal under investigation, and we get that now we have the number of level crossings, and it's nicely divided into a spectral and a level contribution. And again, if we have the number of zero crossings, level crossings, we can find the duration of the mean duration of a fade, and we can find the mean duration of a search simply by using these expressions when we have the CDFs. I'll give one example only. That's for the gamma-gamma distribution, which is the distribution of scintillations in the atmosphere. We stick that into our expression, and we get the probabilities distribution. This is the probabilities distribution for the gamma-gamma distribution, and this is the cumulative CDF for the gamma distribution. And when you have done that, we come up with an exact expression for the number of crossings at a normalized level. Andrew came up with a blue curve, which is a little different from ours, whereas our simulations exactly fit the expression that we derived. So my conclusion is that we have found a simple method with which to increase the accuracy in a fringe-based and line detection system. And we have got 20% increase in accuracy with no bias effect for line center detection. We have a 6 times increase for frequency determination for a fringe-based system, being it in time or space, with a very small bias effect. And the logarithmic transformation didn't give any benefit for deriving spectral transformation. The method might be slightly inferior to a full-blown maximum likelihood estimation, which calls for integrate calculations. And the stipulated results are contingent on having minor additive noise contributions. And last but least, I have made a simple way to predict the number of level crossing for a signal with an arbitrary PDF and spectrum. So thanks for listening. Coffee will be served in your own kitchen.
Thank you very much. It was our last talk today. Please, questions. Professor Mohony, I see.
Yeah. Steen, you very shortly said about the method where you use the singularities. What kind of singularities we use?
The experiments we did, and I say we, it means Wang. And what he did was to take an imagery of the fish in our case, and that has no singularities at all. But then by using a Riesz transform, that's a 2-dimensional Hilbert transform, you can get the imaginary part. And now you have the real part and the imaginary part, and you can go and look for the singularities. And now at each singularity, you know the ellipticity and you know the charge. Now the fish moves and you do the same procedure, getting the new singularities. But you can track, or the name of the singularity is given by the ellipticity and the charge. Therefore, you can pair all the singularities, and by doing this, you can find the movement, in this case, of the fish. So it's based on an incoherent image, which was afterwards transferred into complex signal by the 2-dimensional Hilbert transform, the Riesz transform.
It seems me that these singularities very similar to the C points. Maybe I.
We had no polarization.
I see.
We had no polarization.
I see.
An incoherent image.
I see. Thank you.
Thank you. More questions? There are no questions. Thank you very much again, Professor Hanson. Thus, we have finished today. We will meet tomorrow at 9 o'clock. Our next plenary session will be tomorrow. And the chair of the next plenary session will be Professor Montemezzani. Thus, thank you very much. Have a nice evening or other part of day. Thank you. Goodbye.